we have the binomial probability distribution, and we have tried to identify the p of x is equal to 0 or something else for the given data. And we know that what are all the stuff that we do have with us. Now let me just open the Excel sheet and let us try identifying this binomial distribution. And definitely before we are going to see the binomial distribution, we need to understand what exactly the terms that we do have. Based upon the yesterday's formula, we have, this is how the example represents. There are 5 flights daily, means n is equal to 5. And the probability that any flight arrives late is 0.20, means probability is 20%, which is 0.20. And it is asking the probability for none of the flights are late when p of x is equal to 0. So now let us try how do we use the binomial distribution. So binom dist is the one which you need to use. Number of successes. I want to see the number of successes as 0. Okay. And the trials. How many trials? 5. Why? Because 5 flights are there. None of the flight 0 should be coming late. Probability is 0.20. Comma cumulative. No, it is not cumulative. Hence, it is false. Okay. Enter. 327. 0.327 is the answer. Are you all good with this? Huh? Are you? If you don't understand, I will repeat one more time. Please let me know. Guys, did you all understand this? Whatever that I explained you right now. And also we can do a bit more actually. Yeah, let us take this Excel sheet. First of all, let me know, can you all hear me? I don't see not even a single response. Can you all hear me? Can you see my screen? Yeah, speak out something, right? If you understand, say yes at least. Yeah. So but I don't want to do it something like this. See, let me give you a lot of iterations. Why? Because there is only chances, different chances, like probability of getting 0 flights arriving late. Okay. And 1 flight arriving late, all flights arriving late, right or wrong? We have different types of stuff. So now what I'm going to do, so instead of saying giving 0, let me just use all this stuff. Okay. So that I can expand something like this. Look. Is this good? But how do you understand all this stuff, whether it is right or wrong? If let me see if there is any cumulative, try to identify here. Cumulative. No, we are here. There for cumulative there is a separate example. We can try this example, okay? But before trying this example, let me just open up this Excel sheet and let me say this is a binomial probability distribution, okay? Probability. Okay. And what I can do, I can say make bold, and I can increase this and this. Am I right? Hmm? Okay. And also, I just want to use how exactly this looks like. See, the scarf is something like this. Huh? So let me just. Okay. Can you please tell me, like, is this normal distribution? Is it left skewed or right skewed? Right, good. Okay. Now, shall we go ahead with one more example, guys? Hmm? So instead of having something like this, let me just try to copy and paste this question so that it will be useful. Do you want that Excel sheet, whatever that I'm preparing right now in front of you? If you want, then I will copy and paste this question there itself. But please remember that we are not going to work with the Excel sheets in real time. This is all for your understanding basis. That's it. This is all for your understanding basis on statistics. That's it. Okay. Are you good now? Okay. Right. So what I'm going to do, let me just do something like this. Okay. And what I'm going to do is, so you were asking binomial distribution. Okay. So guys, nothing. This is a formula. Whenever you say equal to binom dist, this will take four different parameters. Four different parameters saying like number means number of iteration. Sorry, number of successes, and next it is number of trials. Next value is probability, and next value is cumulative. Okay. Cumulative represents in a different way. When you say true, it will start cumulative, making the data cumulative. Okay. Cumulative represents in a different way. Okay, it is not the individual values. Okay. So how many of you know working with Excel sheets? Well, why? Because if this is not going to be useful for you, but definitely later in the near future, you will definitely require this once after you become a manager, for sure. So please try to work on this. This is a stuff. This is fine. So now let us take one more example. Shall we go ahead with one more example now? Did I answer your question, Venkat Narayana? Again, we are going to work with the binomial distribution now. Let us work with one more binomial distribution now. I have one more example here. Let me get that example out. Here it is. Okay, so let me just copy and pasting it here. Okay. So for this example, let us study this example. A study in June 2013. What it says something by the Illinois Department of Transportation. Okay, conducted that 76% of the front seat occupants used the seat belts. Okay, a sample of 12 vehicles is selected. What is the probability of the front seat occupants in at least 7 of the 12 vehicles are wearing seat belts? Good question. Guys, can anyone tell me the values associated here? Please, anyone? Get me the values here. See, a study in the June 2003 by the Illinois Department of the Transportation concluded that 76.2% of the front seat occupants used the seat belts. A sample of 12 vehicles is selected. Means what is the N? This is a binomial distribution. What is the sample? Number of successes is different. Sample is 12. Okay. What is the probability? The front seat occupants in at least 7 of the 12 vehicles are wearing seat belts. 7 of the 12 means we have to identify for the 7, right or wrong? 7 successes. Out of how many trials? 12 trials. Okay. What is the probability? 76.2. Hence 0.762. Comma, is it cumulative? Let me first calculate for not non-cumulative, means false. Okay, 0.0902 is the answer. Okay, so but we can also observe here for point p of x is equal to 7.0902. Is it valid? My calculation is valid or not? So let me guys here we should clearly understand one thing, the given values. So this is for p of 7, right or wrong? This is for 7. But what I just wanted to do, I want to give something like this here, 0, 1, till how much? Let me take it till 13. Okay, I know it is 12, but I will take till 13. Okay, and we understand this one. Instead of giving 7, I will say individual. See, it is not able to identify the number here. Okay, doing this, what I will do, that's it. So 13 is not existing now. Got it? So shall we do the probability point for p of x is equal to 8? You can verify 0.1805. Is it tallying? Huh? Next one, p of x is equal to 12.038. Right or wrong? Guys, you need to tell me the answer. Okay, so fine. So now we understand this is non-cumulative. Okay, we will take a cumulative also. Okay, copy, paste. Now let us try the different one. Instead of giving here, what I will give true, and also we'll give something like this. Now look, the value should change. Changed or not? The cumulative, the total number of all probabilities is equal to 1. Should be equal to 1. Huh? Although here, cumulative. Let me just copy. Let me just make it as true. Let me just make it as binomial distribution. Okay. No. Done. Is it 1? Huh? At the end of the day, the cumulative probability. So let me just say cumulative p of x. Okay. I can also make this cumulative x. Wherever I want. One more insertion of what? What I want? I want this one to be represented. That's it. Okay. Guys, are you good? Now, let me just go ahead with this one. this is x and this is p of x. So now I just wanted to see the graphical representation of how exactly it is representing now. So now how is this skewed? Huh? Left skewed. Excellent. Okay. Shall we go? Shall we look at the cumulative? Hmm? Look. Okay. Okay, guys. This is how the graphical representation of the binomial distribution looks like, and these are all the two different examples that we have explored now. Okay. Now rename binomial. Okay. So I'm not required to explain this one. We have just now seen this, and I know like you understood how do we verify this binomial distribution probabilities from the Excel sheet, right or wrong? Hmm? So we have already done with this one, and now hypergeometric distribution. See, in hypergeometric distribution, we have two different types of characteristics. Success. The probability of success is not the same on every trial. Yes. Let me tell you why. Where this hypergeometric distribution usually will be implemented. This will be implemented when there is something like a voter case. Okay, there is a long line of voters where they are standing outside of the polling booth, where they wanted to vote for their own selected party. Outside, we are waiting for asking whoever that they have voted and outside, coming outside, we are trying to ask whether they have voted for a particular party called X. Okay, so whenever the people coming outside one by one in a line, You will ask the first person whether they have voted for the party X. They may vote or they may not vote. If they may not vote, definitely you have to go for the second person. Do you come again for the first person? No. Hence, this is a sampling without replacement. Okay, remember that this is a sampling without replacement, and the probability of success is not the same on each trial. Yes. Okay, and you are waiting for the second person. They didn't vote again. Okay, they are again coming for the third person. So the very first person who will say that they have voted for the party X, the probability of getting a very first success will be calculated. You got my point? You understood? So this is a kind of stuff that you will come across with the hypergeometric distribution. Okay, and also you have to use this hypergeometric distribution when the sample is selected from a finite population without a replacement, and also when the size of the sample is greater than 5% of the size of the population. Means when your population is 100 in number, and when you are trying to identify or do this sample survey with the 10 people, minimum 5 people, more than 5 people, when you are doing this one, minimum more than 5 people. Okay, so here this is how the hypergeometric distribution looks like. This is the formula actually. Okay, this is how the formula looks like. SCX n minus SC n minus S, combinations, different combinations, right? Take a look at this one. N is the size of the population. Capital S, you will have only, guys, you will have only 3 variables here. Okay, 3 variables. Why I'm telling 3 variables? Couple of 2 variables are repeated here. Capital N is size of the population, small n is size of the sample. Okay, and capital S is number of successes in the population, small x is number of successes in the sample, and C is, we know this is a combination symbol. Okay, understand? So now let us see an example. Take a look at this one. Playtime Toys employs 50 employees, 50 people in the assembly department. 40 of the employees belong to a union and 10 do not. Out of 50 employees, 40 people are in union, where 10 they are not in any union. 5 employees are selected at random to form a committee to meet with the management. Okay, regarding the shift starting timings. What is the probability that 4 of the 5 selected for the committee belong to a union? Understand? Means what is the probability of that 4 of the 5 selected? Means they are selecting 5 people. Means out of 5, how many 4 should be from union? From 40. 40 people are there in the union. 40 C4. Right or wrong? Out of 40, you need to pick 4. And out of how many that you need to pick 1? Out of 10, you need to pick 1 again. Okay. So that thing more than that. That's completed. 40C4. Okay. And 10C1 divided by total how many number of selections that you need to make from how many number of people. Total number of workers are 50, out of which you need to select a 5-member team. 50C5. Understand? Shall we look after this hypergeometric probability distribution using the Excel sheet? Here we do have the function. Okay, let us try to work on the same hypergeometric function. In this hypergeometric function, what is the data it is representing here, guys? We need to understand the probability here. Hmm? So we know hypergeometric distribution. Okay. Samples. How many sample? Huh? You want to take 4. Number of samples 5. Population 50. No, 50. Number of population. Here you if you can take a look at this one. Okay. S is number of successes. Okay. Population successes. Okay. And capital N is the size of the population, which is 50. And here we have one more. X is the number of successes. How many? That should be 4, right? I have given it as 4. Okay. N is the sample size or the number of trials. Okay. Here, how much that we have taken as N? 5. Look. Am I good? So shall we run the show here with this one? 431,337. You can see for 4. You can see right or wrong? 431,337. But I don't want something like this. Okay. I just wanted to see for probability of selecting 0. Okay. Probability of selecting 1, 2, 3, 4, 5. That's it. This is a max probability that I just want to see. See, even I can see the probability of selecting 6, 7, something like this also. Yeah, enough. I just wanted to expand. That's it. Nothing more than that. Why? Because selecting 0 candidates is 0. Out of 5, I need to select anyhow. Okay. Like probability of selecting 4 persons out of that union is nearly 43%. This should, you can see, you should observe here. It's almost done. Why? Because the total number of probability of selections is only 5. Okay. So now let us see. If I just want to increase this one to 10, then this is how. Understand? So what I just want to do. Okay, done. So this is what I thought of doing it. So this is completed. Now let us get on to the Poisson distribution. Okay. So coming to the Poisson distribution, generally this Poisson distribution, probability distribution is used for prediction. Okay. This will explain you the number of times some event occurs during a specified interval. Based upon that, we can predict. The probability is almost proportional to the length of that interval particularly. Now let us take a look at this one. Mu power x, we know that mu power x into e power minus mu, e represents the constant 2.71. We know that is a Neperian logarithmic system. According to that, it is e is equal to 2.71. Okay. Next, mu represents the mean number of occurrences or successes. Okay, where x is number of occurrences, p of x is equal to probability of a specified occurrence or specified success. Okay, mu power x into e power minus mu divided by x factorial. Okay, so let us take an example. Assume that baggage is rarely lost by the Northwest Airlines. Suppose a random sample of 1000 flights shows a total of 300 bags were lost. See, generally in airports, bags will be mismatched, and they will be lost and all stuff. So as per the Northwest Airlines, once for a sample of 1000 flights, it shows nearly 300 bags were lost. Okay, hence they have verified the arithmetic mean of the lost bags, where they identified it as 0.3. If the number of lost bags per flight follows a Poisson distribution, okay, with mu is equal to 0.3, find the probability of not losing any bags. Shall we check this one? Huh? So guys, we can always identify the Poisson distribution. So coming to the Poisson distribution, let me just show you here. What is asking for x and mean and cumulative. So here from the given problem, what is x? Probability of getting 0 means no bags were lost. Okay, and mean they have already provided to us. So x is 0, mean is 0.3, cumulative false. Let me just make it false. So 0.740 is the value. Let me try. Right or wrong? 0.70740. But I just wanted to find how many bags lost somewhere like this. As I told you earlier, I just wanted to make it something like this. X and p of x. So if you want me to go ahead till 15 values, and I just wanted to drag this one till 15 values, but before that I need to edit the formula, right? Instead of 0, I will just take down this part. I will expand till here. Okay, and now then I will expand till here. See, it's done. It's already completed. It's almost done. Here, if you can take a look at this one. So this is a Poisson distribution, where I just want to say Poisson distribution. Okay, and I just want to show you this problem, how it is exactly looking like. So you can see, so okay, let me just format this one stuff. Okay, and now let me check the distribution or the visualization for this, how it looks like. How is this? But based upon this one, we all can see how the Poisson distribution looks like, how the binomial distribution looks like, how the hypergeometric distribution looks like. Hmm? Right or wrong? We can be able to analyze different types of distribution, how they looks like. And based upon the data, they will be differing, right or wrong? It will not be the same, guys. So do not think about that all the data will represent the same stuff. Okay. We always look towards achieving some sort of normal distribution, right or wrong? Hmm? You always try to achieve the normal distribution, but whether they comes towards the normal distribution is not, I mean, is different. Why? Because Poisson distribution will show you the curve in one way, and other distributions will show you the curves in another way. You can observe clearly. The cumulative curves are something different anyhow. You all got it? You all got this? Hmm? So this is all what we wanted to cover today. But today I'm going to end up the before I'm going to end up the session. But I just wanted to highlight only one thing today. If at all, how do you identify between the Poisson distribution or the binomial distribution? Whenever your question has an average probability of an event, so the only thing is, like, if your question or if your problem involves average probability, then you try to prefer the Poisson distribution. If you have something like an exact probability, you just try go for the binomial distribution. Good? Are you good? Understand? All of you. Okay, guys, this is what all that I thought of discussing today. Tomorrow, we will discuss the other concepts.